Completely audible. I welcome all to this evening, and we welcome Charles College for his presentation out here. First, let's have a quick introduction what ASHRAE is all about, and then we move on, right? So what is ASHRAE? ASHRAE is the American Society for Heating, Refrigerating and Air Conditioning Engineers, and it has more than 57,000 members in more than 132 countries worldwide, and we have members in from all backgrounds, including architects, from building service engineers, mechanical contractors, building owners, equipment manufacturers, employees, and all others concerned with the design and construction of HVAC and R system in the building. This society here funds their research projects, then offers continuing education programs and develops up and publishes technical standards to improve the building service engineering, energy efficiency, indoor air quality, and moreover, the sustainable development, which is the need of the hour. This year's the theme of ASHRAE Society Year 2020-2021 is the Digital Lighthouse and Industry 4.0. This theme was given by our today's speaker, Mr. Javit's theme. It focuses on the reimagining the building industry and ASHRAE's place in it by integrating not only the industry segments but also the technology. Digital transformation is not simply associated with adopting new technical solutions. Knowledge needs to be captured and linked in such a way that all the relevant stakeholders get benefit out of it. By doing so, it also requires how to collect and store all the data, analyze the data, and make it insightful and actionable. ASHRAE, by and large, there's a disturbance out there. Could you please mute yourself, whosoever is unmuted? Yeah. So ASHRAE is a huge knowledge project. Is there a disturbance out there? Clearly? So ASHRAE itself, by and large, is a huge project. It has lots of technical committees, education, external resources, standards, guidelines, and also it is also into the certification process. Chandigarh is a new chapter that has come up, and we have
I request everybody to please keep your phones or systems on silent, please.
Yeah. So we shall I do something? Mute everyone. So what are the benefits of?
As host, can you force mute everybody?
Yeah, I think I'll have to do that. Is it okay now?
Much better, much better.
Yeah. Right. So why we really call for joining the ASHRAE Chandigarh chapter? First of all, one is access to the e-learning courses that we have, a huge portal, a knowledge-based portal where you can access the learning courses. Then there is endless technical resources. Then we have career and professional development resources. Then there are the global connects with the HVAC and the building professionals. Then access to the ASHRAE technology portal. Then access to the publications and the journals. Moreover, it's a 125-year-old professional technical organization which has members all over the world. The membership fees you can see here. Moreover, it can be seen on the website itself. Today's topic for the webinar is design, build, operate, and maintain. What could possibly go wrong? When we talk of the ASHRAE Code of Ethics, in this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all the real or perceived conflicts of interest. Then we move on to the RP section, which is the research promotion section of the ASHRAE, which this is the most sought after section, considering that ASHRAE is a complete research oriented organization. So the Research Promotion Committee manages and supports both the society level fundraising as well as the chapter level fundraising of the RP campaign. RP is majorly Research Promotion Campaign. Traditionally supporting such research, RP campaign was expanded 10 years ago to include the support of education and the endowed research through the ASHRAE Foundation, YEA, which is the programs, Young India programs, then ASHRAE scholarships, and the general and unrestricted fund. Research, which is the backbone of ASHRAE, remains the primary fund of the program, which is over 2 million raised for this program annually. Starting with this 100 to 150 USD each individual member, then it supports the technical activities, get recognized by ASHRAE, and it supports the visitors to achieve full circle. Here we see the detailed version of the ASHRAE RP fund. Moreover, ASHRAE Chandigarh also has its YouTube channel where you can see all the sessions that we have already conducted. You can go through them, reiterate all the sessions again and again, and gain through it. So let's move on to today's session. Charles Gullidge, 3, PE, DB. He is lead AP and is currently our ASHRAE president. Welcome you, sir, to
If I may ask, could you force mute everybody while I work on getting the screen share started?
So yeah.
Okay, do you see the presentation yet?
To just give a brief about Mr. Gullidge is that he has served in the ASHRAE Treasurer. He has served as ASHRAE Treasurer in Society Year 2018-19. as executive committee and the board of directors. He is former ASHRAE president and director at large. He has served as past chair of the Development Committee, ASHRAE 2011 Energy Modeling Conference, Chapter Technology, Transfer Committee, and Technical Committee 7.1, Integrated Building Design. Mr. Gullidge has received Exceptional Service Award, Distinguished Service Award, Regional Award of Merit, Chapter Service Award, and Dan Mills Technical Awards. Mr. Gullidge has presented multiple presentations on the integrated design topic as an ASHRAE Distinguished Lecturer and the ASHRAE Learning Institutional Instructor. Mr. Gullidge is a senior mechanical engineer with the build, design and build firm of Environmental Air Services Systems LLC in High Point, NC. He has over 35 years of experience in the HVAC industry and a licensed professional engineer in the state of North Carolina, Georgia, Kentucky, South Carolina, Virginia, and Alabama. He has received his BS in mechanical engineering from North Carolina State University. Welcome, sir.
Thank you so very much. Let's see if I can get my screen to share.
Yeah, sure.
Do you see the presentation? It's kicking me out of, it says I am sharing.
Yes, sir, it's visible, sir.
Outstanding. So let's take a journey. I am very happy to be in India this morning after waking up in the United States in North Carolina. It's amazing what is available to us with technology today. Our program today is going to focus on design, build, operate. What can go wrong? And I'm going to fly through these ASHRAE items. We're going to focus on four things: design philosophy, the design disconnects, the build disconnects, and the operate disconnects. And at the end of our session, I hope you will take away an understanding of the difference between conventional and integrated design approach, what unique project fundamentals are and how they apply. And we'll have some fun with some lessons learned on what can go wrong. And trust me, things can go very wrong. So let's start with design philosophy. Conventional design. We're all familiar with the sequential process of what we like to call schematic design, design development, construction documents, bid/procurement, and then moving in construction. This whole process can be equated to making sausage. We just keep packing stuff into the casing and we keep moving it along, and we have people that interact and provide influence, but we just keep pushing the initial start through, and we don't really do anything to optimize that. That is what a conventional design solution looks like. It just keeps building on where it started. Doesn't have a lot of imagination tied to it. And I like to call that, and you'll see this in my presidential theme, the dance of the silos. We are so disconnected, and we've been doing it for years. Just trust us. We know what we're doing, but we know that there are so many barriers to success when we do things this way. The integrated process changes that dynamic. We still flow. I have the opportunity to do a laser pointer. We still flow along in a sequential path. But instead of making the sausage, let's equate it to, let's make pretzels. We're going to challenge everything that happens along this path to make sure we're doing the best thing possible. We have the optimized solution. We have the right solution. And we just keep improving and developing. That is what integrated design is. It involves the collaborative aspect of all the participants on the team to find out what is best. What are the interdependent scenarios that make the whole the best? That is the beauty of integrated building design. So let's look at a philosophy from a standpoint. And let's use net zero or energy efficiency as our vision. This is the pyramid of understanding. If we want to end up at net zero at our conclusion, we have to understand how all of these elements at a foundation level support getting there. So we have to understand, to get to our vision, what is involved to get us to that process. And to make it happen, we start down here. To get to net zero, we are looking at the basic elements of what a building has, how it's occupied, when it's occupied, the number of people in it, the attributes of the envelope, things of this nature. You kind of get the understanding. We resolve from the bottom up before we can achieve the goal we're trying to get to. That understanding is critical in integrated building design. And we're always dealing with four fundamentals: function, form, economy, and time. We play around in this boundary, optimizing what these mean to get that outcome. Function by itself, let me go back a minute. Function by itself is the need and the reason why you're doing something. Form is the response to fulfilling this function, and economy, which is cost of all variations, and time, which is schedule. All of these respond to what is the need for doing what we're doing and why are we building something. So function, form, economy, and time, always keep that in your mind for when you're practicing engineering and dealing with construction and engaging in the built solutions. So let's talk about where this process goes wrong. So we're going to have fun here. This is semi-interactive, but I'm going to give you clues as to a potential scenario, and then I'm going to show you the outcome of the epic buildup I've provided for it. So our first start: attempts to influence adoption of an ASHRAE 62.1 wind-driven rain supplemental blue tarp device have not gained much traction. Perhaps a different color would have done a better job. Take a look at this. This is electric gear, main power gear, and somebody had to put a blue tarp on it because it was located too close to an outside air intake, a louver, a scenario that was not designed to protect against wind-driven rain, so the face velocity through here was way too high. And when it rained and they were sucking air in for the systems, it was just blowing water into the main electrical gear. How do we create that scenario? That's just crazy. Connect end of branch low pressure condensate to low pressure condensate header. That seems pretty simple. This is an actual one of my designers at a point in time with a red line markup of a P&ID for steam piping. Notice this beautiful attempt to draw steam piping at this nice little curvy line here. It was literally interpreted when I said connect the condensate drip leg to the collection header. When I drew it in red with an arrow, it got drawn like this on a drawing that was about to go out on the street. Just crazy. It worked on paper. Tell me how you can possibly build something in 2D scenario with a static drawing with all of these big pipe sizes, 8-inch, 5-inch, 5-inch, 4-inch, all layered as single line, layered on top of more layers of other pipes sitting on top of it. And oh, by the way, there's another layer on top of that in single line fashion, with more details provided on the hookups at the scenarios, and then some more typical details. This is a huge disconnect that ties us to that dance of the silos, where we don't demonstrate constructability. and communicate how something can actually be built. We just put stuff on paper and throw it out there and try to let the contractors figure it out in the field. This is a horrible approach to doing things. This has a high probability of constructability and noise criteria less than 30. I don't think so. Take a look at this mechanical room. There's a classroom. There's a main electrical room. There's another classroom. There's another electrical room with all the telecom equipment. There's a stair. There's outdoors, and there's more outdoors. So these paths in red right here, there's no way to get ductwork for 73,000 CFM of air out into this building. You can't go through the electrical room with all the conduits going up and down. You can't go outside. You can't go through the egress area. And oh, by the way, somebody wanted to keep this. Could I ask you to mute people again, please? You just can't achieve this level of quiet. And this all comes down to a programming scenario. Can I still be heard? Just make sure I'm not muted.
Yes, you're fine.
Thank you. Good confirmation. So this is a disconnect. This is a classical example of conventional design thought where all of the participants were not engaged and a downstream action of bringing people in later once programming had been done to figure out how to do it. It's an unsuccessful scenario. So what exactly did you mean by evenly supported? This really happened. This is a condensing unit. This has a protective barrier over the fins on the condenser coils. Look at these roof supports. These should be lined up where the equipment is designed for the point loading to take place. These got installed in the wrong place. The roof got repaired, flashed in, the equipment got lifted up in the air and set down, and people were standing around going, well, why does it look that way? Somebody looked at static drawings. The way the drawings got plotted, there was like a break line in the drawings right here. That base was on one drawing. This base was on another drawing. Somebody measured those drawings wrong and set one of these in the wrong location, and nobody checked it. And nobody checked this when it was on the ground to make sure that center line spacing was going to work. They put it on the roof knowing it was problematic, and they walked away, and I go up there. That's my shadow. I go up there and find this was left. That's just horrible. Here's a thought. Instead of hot aisle, cold aisle configuration, put your mission critical hat on here. Let's try this. I got invited to an industrial customer to figure out why their servers were cooking and frying. And this is what I walked into. They bought a ceiling fan, kind of a room fan, put it on a pedestal, and tried to move some air around. And they were cooking all of their IT equipment. It's crazy. Absolutely crazy. No design logic. I know exactly what to do to keep debris out of the condenser water pump. Does anybody hear marbles? Now, think hard about this. Marbles in a pump are a dead sign of cavitation within the pump. This is the base of the cooling tower. This is the collection off the bottom of the sumps, and it drops down and goes into these pumps and goes to the building to the chillers. Look at these beautiful strainers located right here at the inlet of the pump. So when we're picking condenser water pumps, we're always having to deal with paying attention to net positive suction head. We get a little bit of free energy, so to speak, just by atmospheric pressure. And then we get this little vertical head here that helps push the pump. And these pumps were actually picked to be at a safe point with their net positive suction head based on this geometry of that head and the atmospheric pressure on the water inside the basin. What they didn't do was pay attention to where they put these strainers to protect these pumps, and the fact that these strainers actually clog up with the garbage that collects in these cooling towers. And you can see this was actually in North Carolina, so there's a lot of pine straw, there's a lot of debris that gets in the cooling tower. These started clogging up, and the pumps started sounding like they had marbles in them, all because somebody put the strainers in the wrong location and didn't deal with capturing the crud in the cooling tower basin to start with. They destroyed some pump impellers. I put in what the engineer specified, insulation per energy code. So what happens when you just put your head in the sand and do what the code says and don't think about building dew point and moisture control and condensation? This is what happens. This is very atypical through hot, humid climate scenarios. Minimum insulation per energy code does not, I repeat, does not address condensation control on cold surfaces. And sure enough, behind a hard ceiling, minimum insulation was put on supply duct that was putting out 55-degree air through the transport path. And it was all raining behind the ceiling, and you can start to see the mold that was starting to grow, all because somebody followed code and didn't do the engineering that should have been applied. But water is getting out. Look, you can see there is water getting out, okay? We all agree there's a little water getting out. Look at the depth of this P-trap right here on the drain pan for the cooling coil. What do you see inside the cooling coil? It's a lake. It's full of water. All of this because somebody, and this happens to be a draw through, so air is going this way through the unit, through the cooling coil, and toward the fan to the left. Nobody paid attention to what the negative static pressure was in this part of this built-up air handler, and they didn't elevate this air handler high enough to get a decent depth on the trap so all the water could drain out. And they had a lake. And that's such a simple thing for us to engineer and avoid. What do you mean I can't size the steam trap at coil outlet line size for 100% outside air application? Well, if you don't pay attention to what you're doing and size the trap for the load and the safety factor, you get something called a busted coil. And all of this happens because the trap, a puny little trap, can't move the condensate fast enough. And look what happens. You get ice and you get a busted coil. So simple to avoid if we size steam traps appropriately for the load with the proper differential pressure, with the proper safety factor. So let's get into the construction side of this. It's not that big of a gap. Okay, that's a debatable point, but this happens to be in a hot, humid climate, and that is the great outdoors. And inside where I am, it's a comfy little space where they're trying to maintain building dew point and temperature control. And look what happens when you have that opening and the differential vapor pressure of the outdoor environment to the indoor environment. The ceiling diffusers were raining all because the moisture level was so high in this space, and the surface temperature of this was below the dew point. And you know what happens when that occurs? It rains. Okay. Great construction. Well, it showed up that way. This is a lab exhaust valve. You don't know whose it is, but you do know that it's got a Harrisite coating on it. Look at this interesting scenario here. On this side, it's a slip fit. And on this side, somebody drove hex screws through the exhaust valve and compromised the herosite coating. This was painful. This is what was supposed to be installed, flanged ends on this and this side. Every one of these, there was about 20 of these valves for this exhaust path. They all had to be ripped out. All this duct had to be reconfigured to get the flange joint on it. And these all had to be replaced, and these all had to be taken out, all because somebody didn't pay attention to what was ordered, what was received, and what got installed. Instead of asking questions, they just moved along. And that's what can happen when you have poor quality control and lack of coordination. So just because you can doesn't mean you should. Well, this is interesting. Look at this beautiful, beautiful condenser water pipe. It's about 18-inch diameter. Somebody came along and cut that section of pipe out, made a half pipe, made another half pipe, re-welded it all together, and then they stuck this really weird pipe saddle off the bottom going this way. This was a major 4,000-ton cooling tower plant for a chiller plant. It used to have side stream centrifugal separation and zero water loss component. And it was working so well that the facility manager got tired of pulling bags out and disposing of the debris like it was supposed to do, and it was keeping debris out of the cooling towers. He paid somebody to come in and rip all that out and put a sand filter in blowdown scenarios. This location happens to be after the fourth of 4 cells, so the water volume is the biggest, the flow rate is the largest, and when they put that sand filter in and changed the dynamics, because they did, here are the consequences. All of the nozzles they put in and sucking all the water out at a much higher velocity at the point they did, they sucked the towers dry. They dumped all of the chemical dispersion that was taking place inside the loop of the condenser water. They were getting air into the collection. They were cavitating the pumps because there was truly now air inside the system. All of this was exposed, and the residency time of the chemical treatment was gone. And look at all the green stuff growing inside the cooling tower. Not a good scenario. You have to look at your velocities of what you're doing with condenser water so that you don't suck a tower dry. And you've got to be careful with what you're doing with the chemical treatment so that you're not wasting it and dumping it to drain. And you propose changing the compressed air filters. How? Well, take a look at this. This is really nice ductwork, and this is nice looking compressed air piping. But look at the brilliance of this moment. These filter cartridge assemblies have to be removed out the top. This got located right underneath where a supply diffuser was on the trunk inside the mechanical room. How do you do that? How do you get away with doing that? It had to be redone. Oh, you were serious about the lagging extensions. Okay, remember the conversation I had about minimum insulation thickness? Chill water systems are cold. Hot, humid climates don't like cold, and to avoid condensation, you have to have thicker insulation. When you put this kind of thermowell into the pipe where this part screws into the weldolet, that's all you've got sticking in, and your insulation projection is out here. I had 100 of these I found that were being installed on a manufacturing facility where somebody cut a corner and didn't put the lagging extensions in so that this part could be outside the insulation. A lot of rework, a lot of waste required to deal with something that had a purpose. I can't find this in SMACNA or ASHRAE. This is special. And yes, that is stainless steel. And would you like to see what it's connected to? That's the back of a fume hood. And look at this brilliant workmanship. How do you even quantify the pressure drop getting air from this hood through the exhaust path to get to the fan? All of this was created by somebody had the brilliant idea late in the game that instead of the fume hood being located vertically straight down where it was supposed to be, somebody's cabinet layout wanted to modify it, so they moved it in the field, and the plumbing gases for the hood all got reworked, and the mechanical came back and did this. Brilliant. Obviously, we had a problem with flow on that hood. Lighter than air, you say? Okay, you can see the top of a bottle tank here, and we got some action going on, and this gas happened to be lighter than air, so the exhaust got put in the correct spot for that room. But look at this conduit. Where does this conduit go? I wonder where it goes. Oh, it goes to the gas sniffer that's associated with this level of gas that once it leaks, it collects high in the room. Well, they had to rewire this and move the gas sensor up to where the danger detection zone was for the gas in question. Has anybody seen my ladder? So let me tell you this right off the top. Refrigerant piping is not a fair substitute for a ladder. Somebody used this piping on this refrigerant circuit. This happened to be like a 40-ton condensing circuit. They used it for a ladder to get up here to see something, and they obviously cracked some of the solder joints on this, and we lost about 40 tons capacity worth of R410. Just crazy, just because somebody thought it made a good ladder step. Differential pressure transmitter, you say? Are those hardwired? So take a look at this. This is the filter section for a built-up air handler. You can see the frame configuration for where the filters slide in, and they slide in through this door. And for this client, this filter station was to have a combination gauge transmitter. Well, look at where they put the transmitter. They put it in the door. So the door has to open up, and there's no way to keep the probes and the wiring intact that are on the upstream and downstream side of the filter. This should have been placed here in a fixed surface, and the tubing put upstream and downstream of the filters. But no, somebody put it in the moving door. Just very impressive. You want me to do what at the VFD while the fan is running? Who here among you would climb into an air handler that's running on a 20,000 CFM air handling unit with this big double width, double inlet centrifugal fan running with a belt, and put your posterior up against this to get to the drive to look at it and see what it's doing? Nobody would. This was crazy that something showed up this way. Who needs pipe for drainage when good old Raceway will do the job? Trust me, there is a drain over there somewhere. Look at this beautiful workmanship to try to channel water where it could go. Very creative. Primary secondary decoupler redefined. Okay, we all understand primary secondary pumping and how we have the decoupler section of the pipe. Do you think that might serve that purpose? That is craftsmanship to even build something like that. And you have to believe me that that is a primary secondary decoupler if you followed all of these octopus legs out. Crazy. It didn't work. What do you mean by wiring conduits have to be sealed airtight? Nobody does that. Okay, that's fair. But when you're doing freezers and you don't seal the conduits or any opening that comes inside the freezer, look what happens. I had an argument with the electrical side of the company I used to work for about this discussion of vapor pressure inside a why is that doing that? Vapor pressure inside a freezer is so much lower than vapor pressure outside in a hot, humid climate. Moisture is going to push its way into this inside environment here. And just a simple unsealed electrical conduit that communicates outside of this box, there's enough moisture in there that you start making an ice dam. So they had to come in here with a blowtorch while this was operational, melt this ice off, get in there to seal that before it would stop doing it. Just an understanding of what vapor pressure differential means and the environment you're working with, getting back to those form issues in response to function. Oops, my bad. That used to be a fan coil unit. You can see the impaled fan coil unit. You can see the beautiful mushroom exhaust fan that was also wiped out in the process. Lay down areas on construction sites bring risk, and there's nothing you can do about it except move your equipment off-site and get into off-site modular construction to keep this scenario from happening. Let's move the fume hood connection instead of reworking the duct. So you remember those beautiful duct fittings I showed you earlier? Look at what was attempted with the hood itself. Somebody tried to deal with another hood that moved by, we're only 6 inches away. Let's just cut the opening that used to be here and move it to the left a little bit. And look what happens. These fume hoods have such a thin mill thickness on their stainless steel sheet. It is not very conducive to coming back and welding. It was tried, and this whole entire hood was ruined, all because somebody wanted to move something 6 inches and didn't deal with the ramifications downstream of what that meant. Brilliant. Who needs flanges in insulation? Another modular air handler. These happen to be chill water coils, big unit, stacked chill water coils. Well, this might be an interesting development. That right there is a blow up of that. Look how close that is to the wall. That was 2.5-inch piping. There is no way to get a flange on this, to go to flanged piping, and there's no way to get in here and insulate this with, I think that required 2-inch insulation to get to it. How do you work on it? Big disconnect. Yikes. So don't do things like this in your design practices. I understand this was done for temporary to deal with construction, but how do you make air go through all of these gyrations in flex duct and get air in? You're going to get something. This was an attempt to keep air flowing, but even though it's creative, it's crazy. Ever wonder why roadway bridges use steel for their support beams? Obviously, so that fiberglass cooling towers won't damage them. Yes, that used to be a fan and the fan cowl on a fiberglass cooling tower coming to a process. Nobody paid attention to the height of the flatbed, the height of this, and how they had it on top. It had no escort. They had no poles going down the highway, and they went underneath a low bridge. They sheared it off, and it still showed up to the job site and wasn't going back to the factory. I thought that was kind of special. Put a level on the roof, please. Okay, this is not an optical illusion. That is a flat roof curb with a very large rooftop air handling unit. Actually, it's a DX large rooftop unit. This back here is the actual penthouse of the mechanical room. And you can visualize along that top edge what level should be. You can obviously see this thing is sloping downhill, all because somebody didn't measure and understand what the pitch of the existing roof was before they put this up. They ordered a flat roof curb with no pitch to it, installed the curb, flashed the curb, put the unit on the roof, and then we're wondering what to do about all the cooling coil condensate downstream of the evaporator coil that was overflowing the drain pan and falling down in the building. Really, this happened. This really happened. MERV 15, no problem. Okay, if you're going to do MERV 15 filter, just go all in and go higher with MERV 16. We had a customer that wanted MERV 15 for some crazy reason. You can't find MERV 15 filters. We had to have a salesman travel the country trying to scarf up MERV 15 filters, threw them in his car and drove them to the job site. Pay attention to availability on what you're trying to do with filtration, especially in these days of COVID response, where ASHRAE is suggesting that you start looking at minimum MERV 13 and 14 filtration instead of MERV 7 and MERV 8. Availability, understanding availability is important. Steam hammer, you say. Here's another busted steam coil and an attempt to try to fix it with liquid copper. Doesn't work. Why does it happen? Because people do not pay attention to getting the outlet for the steam coil happens to be right here. The trap does not have enough vertical height on outside air to get the condensate that collects. If the condensate can't get out fast enough, the condensate collects, and on 100% outside air, you're actually going 100% steam, and you're modulating the space and bypass dampers for control. It's not really a soft start scenario. That will all hammer, and the shock wave will destroy a steam coil. All right, let's move on. 480 volt and applied recycling. Brilliant. Yeah, somebody took some bottles, cut them off, and used that to stick 480 volt wiring into. That's just beautiful. All right, let's talk about operations. The owners are not safe in this world either when it comes to integrated understanding. What do you mean by it eats aluminum? Folks, that used to be a coil. You can see the copper tubes. You can see aluminum fins. And we're missing some aluminum fins down here. This was a life safety client, and they deal with blood pathogens. And they use, and I won't name it, but they use a special product to clean surfaces to deal with the fact that they do have blood, and you worry about pathogens being transferred around. And this chemical that's used is aggressive to aluminum. So when it gets in the airstream, especially when somebody steps inside the air handler and sprays it on the coil, look what happens. Major disconnect between how this owner operated in response to the need and the engineering community not understanding a basic formed fundamental associated with these coils needed to have something different than classic copper tube and aluminum fin. It worked just fine last week. Oh my, that looks dirty. I hope you like the fact that I've liberally used ASHRAE logos to hide commercialism interest. Oh, I see daylight on that roller. I see hydraulic oil on this plate right here. This was a desiccant dehumidifier, an industrial desiccant dehumidifier. We were asked to come in and do something downstream of where this served to reapply it. We reapplied it and tried to make it do what it was supposed to do based upon what it should do, and found out it couldn't do what it needed to do. And then we went back and looked at the equipment, and we found all these filters completely clogged, completely dirty, the desiccant drum not able to turn because it wasn't getting traction on the rotating wheel that turns the drum, and the crank that actually turned that shaft was leaking fluid. So this baby was in horrible shape. Lesson learned: make sure stuff is in good shape and does what it's supposed to do if you're repurposing it to do something else. Have I got a deal for you? Look at this beautiful torched steel and this lovely pipe that's been sitting outside and corroding. This was an industrial customer who had a cooling tower installation, not just the towers themselves, but the entire framework to support it at one location in the United States, and they wanted to move it to a plant in another location in the United States. So nobody took any dimensions, any measurements, any photographs of how it all went together. They just went and torched it and started shipping pieces to the other site. And it sat out on that site for about 6 months before it ever got utilized. And it got so corroded with iron oxide from just sitting out in the elements, and nobody knew how to put it back together without doing a lot of forensic look to figure it out. Just not a good scenario. It's 15 feet up in the air and between the crane rails. It will be safe. I beg to differ. That is a fan. That is a filter on the inlet. That's the discharge. This platform was 15 feet in the air. The logistical supply team working inside this plant was riding around with their forklifts elevated at high speed, and somebody wasn't paying attention, and they drove a fork right into the side of this. Picture this being oriented. You can see the footprint for where that point right there should have been mounted right here. They hit that with a fork, sheared all of these off, and rotated it, and made a big mess, all because of unsafe operation. Why is my fan wobbling? That is a fan. That is dirt. That is grime. They obviously had a problem with the fan wobbling, associated with the fan wheel being dirty and out of balance. What was their solution? Let's just replace the bearing that got damaged and not deal with the source problem of a wobbling fan and shaft. Pretty good solution. It's going to be temporary. On the surface, this seems innocent enough. Look at this beautiful air rotation unit, chill water piping, A-frame coil, industrial quality deep throw drum punka louvers. There are 3 high volume propeller fans in here. This is full of filters. There's an intake right here, and there's an economizer that comes in low. This is a pretty cool setup. And then you open one of these doors right here, and you see filters that look like this. We got called in to look at one of our design installations, and there was a problem with this air rotation unit. We opened it up, found the filters had collapsed. Now I want you to be, I hope you can pick up on this. This side of the filter looks dirty, and this side of the filter looks dirty, we discovered that they were turning the filters over when the upstream side got dirty to put the downstream side now on the upstream side to load that side of the filter. These filters had collapsed. I wish I could have gotten a picture inside, but I couldn't. One of these filters got sucked up into the propeller fans that sat in this area right here, destroyed one of the propeller fans, all because somebody did not understand what proper filter maintenance was and when filters needed to be changed. This day is not starting out well. You can imagine with all the water you see on the floor and all the cans that are collecting the drips and the fact that a ceiling tile is missing now and an expensive copier is underneath that, this is not a good day for somebody. And I got called to the carpet to explain myself with what were you doing? Why does your system not work very well? And it all came back to an air handler sitting above this space where the filter had gotten so dirty it had actually collapsed, and this was the position it was found in. There was enough static pressure between the filter and the fan that was holding all of the chilled water, the condensate off the coil in the drain pan from all getting out. And when that filter collapsed, all of the water that was going to my right that was in that drain pan overwhelmed the drain point that it was going to, and it all flowed out into the office. That was a fun day. This could be a clean, good manufacturing process issue. Remember that P-trap on the cooling coil condensate drain pan? Well, this is a better picture of that same drain pan. Look very closely at what's happening inside this area because this environment has been neglected for so many years. This was in a good, clean manufacturing process scenario, and the airstream going to critical space was all exposed